All right, on to 3.6. So this is a moment that many of you have been waiting for. If you've had calculus before, like some of you are repeating this course for various reasons, but so if you've had this course before, then you know all about L'Hopital's rule and how it makes calculating certain types of limits a lot easier. So we're going to introduce L'Hopital's rule to you now. L'Hopital's rule deals with computing limits of certain limits that have particular kinds of indeterminate forms. And we've used that word a lot, but we're going to try to kind of give it a little bit more of a definition now. So this is an informal definition, but anyway, here it goes. So the limit of an expression that has one of these forms, f of x over g of x, f of x times g of x, f of x to the power of some other function, f of x minus g of x, f of x plus g of x, is called an indeterminate form if f of x and g of x exert conflicting influences on the limit. So in particular, right, these scenarios are indeterminate. So if if like f is going to 0 and g is also going to 0, that's an indeterminate form. Okay, you can't tell where the limit of the quotient is going to go. Same thing if you have if f is going to infinity and g is also going to infinity, that's indeterminate. If you have a 0 times infinity type of situation, where one of the functions is going to 0 and the other is going to infinity, well, then they're competing with each other, and it's hard to tell what's going to happen to that limit. 0 to the 0 is indeterminate. 1 to the infinity is indeterminate, right? That's maybe a little bit confusing, but just keep in mind that we're not actually saying 1 to the infinity. We're not saying like 1 times 1 times 1, infinitely many times or whatever. We're saying some function is getting closer and closer to 1, while another function is getting closer and closer to infinity. And so it's impossible to say what happens there. Infinity to the 0, indeterminate. Infinity minus infinity is indeterminate. When I say that it's impossible to determine what's happening, it's not actually impossible. It's just that it requires a little bit of algebra, a little bit of ingenuity to kind of rework the expression to get it so that it's not in an indeterminate form. So let me give you a clear example of this, right? So for example, limit as x approaches 0 from the right of x times ln of x is an indeterminate of type 0 times infinity, right? Because as x approaches 0 from the right, x is going to go to 0. ln of x is going to go to negative infinity, right? Right? If you think about what the natural log function looks like, it looks kind of like that. So as you're approaching 0 from the right side, f of x is going to go into negative infinity. So this is 0 times negative infinity. Okay? So it's an indeterminate of type 0 times infinity. So I guess I should mention that in all of these scenarios, infinity could be positive or negative in each of these cases. So like a positive infinity over a negative infinity is still indeterminate, right? 0 times a negative infinity is still indeterminate. Okay, on the other hand, this function is not indeterminate. So if we're looking at limit as x approaches infinity of square root of x times 1 minus x squared. Well, as x goes to infinity, square root of x goes to infinity. And 1 minus x squared goes to negative infinity. So this is a positive infinity times a negative infinity. Well, those aren't exerting conflicting influences. They just combine to make negative infinity, right? The limit here would just be negative infinity. So this one is not an indeterminate form. Okay. So the only indeterminate forms really are these ones up here. Okay. So with that in mind, now let's talk about L'Hopital's rule. So L'Hopital's rule tells us that if f and g are differentiable on an open interval containing a, except possibly at a itself, right, so they're differentiable, And also suppose that limit as x approaches a of f of x over g of x is an indeterminate of type 0 over 0 or infinity over infinity. Okay? If that's the case, then limit as x approaches a of f of x over g of x equals limit as x approaches a of f prime of x over g prime of x, provided that this limit exists. That is, you can take the derivative of the numerator and denominator independently of each other. So this is, you're not going to use the quotient rule here. You're just going to take the derivative independently of the numerator and the denominator, and the limit of the original functions turns out to be the same as the limit of the quotient of the derivatives, provided that the limit exists. Okay, but it's important that it has to be, in order for this rule to apply, the quotient that you're looking at to begin with has to be an indeterminate of the type 0 over 0 or infinity over infinity. Otherwise, L'Hopital's rule does not apply. So what I want to do is give you several examples. I've got, I think, like 12 examples to show you. So let's do it. Okay, let's find the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay, if we try a direct substitution on this, we're going to get 2 squared minus 4, so that's 4, that's 0 in the numerator, and then in the denominator we're going to get 0, right? So this is an indeterminate of the form 0 over 0, and that means L'Hopital's rule applies. So, so we can apply L'Hopital's rule to this. We can say, well, this equals, and I'm going to write an LH above the equal sign every time I apply L'Hopital's rule. But so this equals the limit as x approaches 2 of the derivative of the top. Well, derivative of x squared minus 4 is just going to be 2x, right? Over the derivative of the bottom. Derivative of x minus 2 is just going to be 1. And now if you plug in 2 for x, you get 4, right? Okay, so that's how L'Hopital's rule works. Now notice that these kinds of limits we could compute before. What we did is we would factor cancel off the common factors. And sure enough, you know, we end up with the same answer. Okay, but now we just have another tool that helps us arrive at the answer, and this tool is very powerful because it helps us calculate limits of things that we couldn't necessarily do some kind of algebraic manipulation on. Okay, let me give you another example. Let's find limit as x approaches 0 of x squared minus 4 over x minus 2. Okay, now before you get overzealous and immediately start taking derivatives, this is not an indeterminate. This is not an indeterminate form. You're not going to use L'Hopital's rule on this, right? Because if you just do direct substitution here, what do you get? You get 0 squared minus 4 is negative 4 over 0 minus 2 is negative 2, right? You just get positive 2. That's not indeterminate, so you don't need to use L'Hopital's rule. If you did use L'Hopital's rule, you would end up with the wrong answer, right? If you use L'Hopital's rule, you end up at this point, and then if you plug in 0, you just get 0, which is not correct. Okay? So, moral of the story, only use L'Hopital's rule when you have an indeterminate of the form 0 over 0 or infinity over infinity. Okay, let me give you another example. So let's do limit as x approaches 0 from the right of ln of x over cosecant x. Holy schmoly, who wrote this problem? Actually, I think I copied it from your book, so this is your book's fault. But let's think about what's happening here. As x approaches 0 from the right, ln of x is going to go to negative infinity. And what's going to happen to cosecant x? As x approaches 0 from the right, So cosecant x, it's like a bunch of parabolas. It has asymptotes there at 0 and at pi, right? And then it kind of looks like this, right? And then it just repeats this over and over again, like that, right? So that's what cosecant looks like. So as you approach 0 from the right, cosecant x is going to be going to positive infinity. Okay? So we have a negative infinity over positive infinity case. This is indeterminate. This is indeterminate. It's an indeterminate of the type infinity over infinity, which means that L'Hopital's rule applies. So I'm going to apply L'Hopital's rule. So derivative of ln of x is 1 over x. Derivative of cosecant x is negative cosecant x cotangent x, which is how nasty, right? Okay, so let's see if we can clean this up, because if we plug in 0 at this point, we're still going to get infinity in the numerator, or negative infinity in the numerator, and in the denominator, holy schmoly, what would we get? Negative cosecant is going to go to negative infinity now. Cotangent, ooh, where does cotangent go? Cotangent, I think, looks kind of like this, right? So it's also going to pop. So I think this is going to be infinity over infinity. It's going to be an infinity over infinity situation, which is indeterminate still. But I'm not sure I want to apply L'Hopital's rule yet. Let's try to clean it up. Maybe I do, actually. No, I don't. I want to try to clean this up. I'm going to call this negative 1 over x times cosecant x times cotangent x. Now what's this? This is going to be a 1 over 0 times infinity type of situation. That's still indeterminate. I could use the reciprocal identities here. Or maybe write them in terms of sines and cosines or something. Let me see. I kind of don't like that 0 in the denominator. That causes problems, right? Well, secant is 1 over cosine, tangent is sine over cosine, so this is sine over cosine squared. Does that help? Well, now this is 0 over 0. I think I'm spinning my wheels. I think I'm going in circles, and so it might be best to go ahead and just apply L'Hopital's rule again. Right, because if I plug in 0, I get sine of 0 is 0. Down here I get 0 times cosine of 0 is 1, so I get 0 over 0. So this is indeterminate of type 0 over 0. You know, I'm going to go ahead and apply L'Hopital's rule. So derivative of sine is cosine. In the denominator, I'm going to have to use product rule, right? Derivative of the first times the second plus the first times the derivative of the second. That's 2 cosine x, and that involves chain rule, right? So it's going to be 2 cosine x times negative sine x. Holy schmoly. But I don't have a 0 over 0 anymore. I don't have an indeterminate form anymore. When I plug in 0 here, I'm going to get 1 over 1 plus 0. Right? Because 0 times anything is 0. So, right, this would be 0 times 2 times 1 times 0. Right? So it's just 0. So I think this is just negative 1. I'm sure there's a shorter path to get there. Holy schmoly, that shouldn't have taken me so long. Maybe if I had just... So up here, this was already indeterminate. It was infinity over infinity, right? So maybe if I would have just applied L'Hopital's rule again, just immediately, I could have gotten here quicker. But whatever, this worked. Whatever gets the job done. Okay. So negative 1 is the answer to part C. But this is an important thing, right? It's like, so we used L'Hopital's rule twice, and you're allowed to do that, right? You're allowed to just keep applying L'Hopital's rule as long as what you have is truly indeterminate, right? So it has to be an indeterminate of the form 0 over 0 or negative or infinity over infinity, right? In order for L'Hopital to apply. Let me give you another one. Let's do limit as x approaches 0 of sine 2x over x. If I plug in 0, I'm just going to get 0 over 0. So I can apply L'Hopital's rule. Right? I get 0 over 0. So I'm going to apply L'Hopital's rule. So this is going to be equal to the limit as x approaches 0 of derivative of the top would be cosine 2x times 2. Right? So cosine 2x times 2, because of the chain rule. The derivative of the bottom would be just 1. So that's not indeterminate, right? If we plug in 0, 2 times 0 is 0, cosine 0 is 1, 1 times 2 is 2. So this is just 2. That was much easier than the previous problem. Okay, let's do another one. Limit as x approaches pi over 2 of 1 minus sine x over cosine x. Let's see. If we plug in pi over 2, sine of pi over 2 is 1. 1 minus 1 is 0. Cosine of pi over 2 is 0. So we're getting an indeterminate, 0 over 0. So let's apply L'Hopital. Okay, so this is going to be limit as x approaches pi over 2. Derivative of sine is cosine, right? So we're going to have derivative of 1 is 0, and then derivative of negative sine is, I guess, negative cosine. So we're going to have just the negative cosine x in the numerator. In the denominator, derivative of cosine is negative sine. Okay, so obviously the negatives cancel. If we plug in pi over 2 now, cosine of pi over 2 is 0, but sine of pi over 2 is 1. So this is just 0 over 1, which is just 0. That's not indeterminate, right? That's just 0. Okay, I don't know why I put a check mark on on that one, but there you go. I guess I was just feeling extra good about that one. Alright, here's another one. Let's look at limit as x approaches positive infinity of x over e to the x. Go ahead and give the video a pause. See if you can try this one out on your own. If you haven't been pausing the video between each of these examples, start doing that, right? When I give you examples, feel free to pause the video and try to work it out on your own before I just give the solution to you. Okay. So here's what I'm going to say about this. If I plug in infinity, I'm going to get infinity over infinity, right? This is a pretty clear case of an indeterminate of the form infinity over infinity. So I'm going to use L'Hopital's rule, and I'm going to write this as limit as x approaches positive infinity of derivative of x is 1. Derivative of e to the x is just e to the x. Now if I plug in infinity, I just get 1 over infinity, which is 0. That's not indeterminate, right? That's just 0. Okay, another one. Let's do limit as x approaches 0 from the left of tangent x over x squared. Give the video pause and try it out on your own. Okay, if we plug in 0, tangent x goes to 0, right? Tangent of 0 is just 0. And x squared is also just 0, so this is 0 over 0. It's an indeterminate form 0 over 0. So I can use L'Hopital. Derivative of tangent is secant squared. Derivative of x squared is 2x. Now, if I plug in 0, secant of 0 is 1. So secant squared of 0 is also 1. 2 times 0 is 0, so this is like a 1 over 0 situation. 1 over 0 is not indeterminate, but you do have to figure out, are you approaching positive infinity or negative infinity? So think about it like this. We're approaching 0 from the left. That means we're plugging in negative values to this expression here. Secant looks like this though, right? Right? It does this thing, right? And copies over and over and over again. So when we plug in a negative value that's close to 0 into the secant function, we're going to get positive values back, right? Like the y values here are all positive. But when we plug in negative values to 2x, we're going to get negative values. A positive divided by a negative is going to be a negative. And so this thing's going to shoot off to negative infinity, for sure. Okay. Okay, I have two more for you. Let's do limit as x approaches 0 of 1 minus cosine x over x squared. Okay, if we plug in 0, cosine of 0 is 1, so we get 0 over 0, right? Definitely we can apply L'Hopital. Derivative of 1 minus cosine x. Well, the derivative of cosine x is negative sine x, so it's going to be negative sine x, or in other words, just sine x. Derivative of x squared is 2x. I feel like we've done this before, didn't we? We must have done one very similar to this, but anyway, we get sine x over 2x. Now if we plug in 0, we get 0 over 0 again, which is indeterminate, right? So again, we're getting 0 over 0. So I'm going to apply L'Hopital's rule a second time. So this is going to be limit as x approaches 0 of derivative of sine x is cosine x, and derivative of 2x is just 2. So now when I plug in 0, cosine 0 is 1, I just get 1/2. Okay. So that's another example where we use L'Hopital's rule repeatedly. And one more. One last example. Let's do limit as x approaches positive infinity of x to the negative 4/3 divided by sine of 1 over, oh man, I don't know if I want to do this. Sine of 1 over x. Okay. Go ahead and give the video a pause, see if you can work it out. Okay. So, as x gets really, really large, x to the negative 4/3 is the same thing as 1 over x to the positive 4/3. And as x gets really large, 1 over x to the positive 4/3 is going to get really, really small. So the numerator is going to 0. What's happening in the denominator? Sine of 1 over x. As x gets really large, 1 over x gets really, really small. It gets close to 0. And sine of 0 is 0. So this is an indeterminate of the form 0 over 0. So we can apply L'Hopital's rule. I have a feeling this is going to get messy. This is limit as x approaches positive infinity of negative 4/3 x to the negative 4/3 minus 1 would be negative 7/3, right? Over. Derivative of sine of 1 over x is going to be cosine of 1 over x times the derivative of 1 over x. 1 over x is the same thing as x to the negative 1, right? So its derivative is going to be negative x to the negative 2. Or if you prefer, you could call it negative 1 over x squared or something like that. Okay, that's really interesting. Now as x goes to infinity, this thing is still going to go to 0. 1 over x is still going to go to 0. But cosine of 0 is 1. Okay, so I'm kind of thinking this is like 0 here, 1 here, and now what's this guy? This is 1 over x to the positive 2. 1 over x to the positive 2. As x gets really large, 1 over x to the positive 2 is going to get really small. This is going to be 0. Okay, so this is a 0 over 0 again. It's another indeterminate of the form 0 over 0. But I do wonder if I can... I can simplify it at least, make our lives a little bit easier by canceling some of those x's, right? So negative x to the negative 2, I can move that up here and call it negative x to the positive 2. And for one thing, the negatives will cancel. But for another thing, x to the positive 2, 2 is 6/3, right? 6/3 minus 7/3 is 1/3. So I think this is going to be 4 x to the 1/3 over 3 cosine 1 over x. That's a little bit nicer. And in fact, this is not even indeterminate anymore, is it? Because now when I plug in infinity, I just get infinity. Oh, it's because it should be a negative 1/3. Never mind. Now it's 0 again. So this is 0, but this is cosine of 0 is 1. This is 3. Okay, so it's not indeterminate, right? This is just 0 over 3, which is 0. Right? Does that make sense? When you plug in, I don't know why I'm asking you if it makes sense. You're not here, but if you plug in infinity, a really big number to a negative exponent is going to be 0, right? If you plug in infinity here, 1 over infinity is 0. Cosine of 0 is 1 though, right? 1 times 3 is 3. Yeah, so you just get 0. So there you go. There's that one. Oh. So, I have a little bit more to say about L'Hopital's rule, but you've seen a bunch of examples. A couple of things that I want to point out. So something like limit as x approaches positive infinity of x to the n over e to the x. So if you're comparing like a polynomial to an exponential, the exponential is always going to grow a lot faster than the polynomial, right? It's going to dominate. And so polynomial over exponential, as x goes to infinity, that's going to go to 0. On the other hand, if you switch it up, exponential over polynomial, and take the limit as x goes to infinity, that's going to shoot off to infinity. Now here's why that happens, because if you imagine plugging in infinity, you get an indeterminate of the form infinity over infinity. So you can apply L'Hopital's rule. But what are you going to get when you apply L'Hopital's rule to this? You're going to get n times x to the n minus 1. And down here you're just going to get e to the x, because e to the x is its own derivative. Well, that's just going to be infinity over infinity again, right? So you apply L'Hopital's rule again. and you get n times n minus 1 times x to the n minus 2 over e to the x. That's still infinity, right? So you keep doing this over and over again, until you've taken the nth derivative of x to the n. Now when you take the nth derivative of x to the n, what do you get? You get n times n minus 1 times n minus 2 times n minus 3 and so forth all the way down to 1. And you may be familiar with the factorial, right? That's n factorial, okay? Meanwhile, the nth derivative of e to the x is always just going to be e to the x, right? So when you get it down to this point, you're going to have just a constant. So by the time you've taken n derivatives of this thing, you're just going to have a constant in the numerator, and then you're still going to have an exponential in the denominator, right? So clearly, when you plug in infinity there, you're going to have a constant over infinity. That's just going to be 0. Or in this case, you'd have infinity over a constant, and that's just going to be infinity. Okay. So that's one comment. The other comment that I want to make is that indeterminates of the other forms that we've talked about, right? 0 times infinity, infinity minus infinity, or these three things down here, 0 to the 0, 1 to the infinity, infinity to the 0, we can usually fix them up so that we can apply L'Hopital's rule to them. Okay? And remember, for L'Hopital's rule, they have to be in the form 0 over 0 or infinity over infinity. But we can usually force these things to be in one of these formats. And I'll give you some examples to show you how we do that. Okay, so let's do limit as x approaches 0 from the right of x times natural log of x. We've already looked at this one, right? This is 0 times negative infinity. So it's an indeterminate of the form 0 times infinity. But we can fix it up, right? Here's kind of the standard trick. So what we're going to do, so this is 0 times infinity, right? So what we're going to do, we're not going to apply L'Hopital's rule to it. Obviously, we can't apply L'Hopital's rule when it's in this format, but what we can do is we can rewrite this as ln of x divided by 1 over x. And hopefully you'll agree that this is the same thing as that, right? Because if you take the denominator, you flip it, you multiply, well, you just get x times ln of x, right? So these two things are the same, and that's sort of the standard trick. Because notice what happens now when I plug in 0, this is going to be infinity, negative infinity, and this is going to be positive infinity, right? So it's an indeterminate of the form infinity over infinity now, which means I can apply L'Hopital, right? So derivative of ln of x is 1 over x. Derivative of 1 over x is negative 1 over x squared, right? It's x to the negative 1. You take the derivative, it's going to be you pull down the negative 1 and then make it a negative 2. So anyway, so that's that. Now if I plug in 0 again, I'm still going to get an infinity over infinity type of thing, but I can simplify this now, right? I can simplify it and call it, I can take the negative sign out here. If I flip and multiply, I would get x squared over x, or in other words, negative x. Okay? And as x approaches 0 from the right of that, well, it's just going to be 0, right? So this is just going to be 0. So that's how we tend to fix up these kinds of things. Let me give you a few more examples. So let's do limit as x approaches pi over 4 of 1 minus tangent x times secant of 2x. Okay. Go ahead and give the video a pause. See if you can try that one out. All right. Here's my solution. So when I plug in pi over 4, tangent of pi over 4 is 1. 1 minus 1 is 0. So this is 0. 2 times pi over 4 is pi over 2, and secant of pi over 2, remember secant looks like this, and it has this vertical asymptote at pi over 2. So secant of pi over 2, as x approaches pi over 4, actually, it depends on if we're approaching from the left or from the right. From the left, we'd be approaching infinity. From the right, we'd be approaching negative infinity. So I'm not sure, but I'll just call it infinity. All right? It's an indeterminate of the form 0 times infinity in either case. So let's see if we can fix this up so that we can apply L'Hopital's rule to this somehow. I'm thinking if we do the same trick as what we did before, we would call this secant 2x over 1 minus tangent x. But I'm not sure that I want to differentiate 1 over 1 minus tangent x. I wonder if I just write this in terms of sine and cosine. Like cosine of 2x. Secant is 1 over cosine 2x, right? So I'm thinking, what if I rewrite this? Maybe this won't lead anywhere fruitful, I don't know. But what if I rewrite this as 1 minus tangent x over cosine 2x? Okay. Well, pi over 4. So 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0. So yeah, this worked out nicely, right? Because now I get an indeterminate of the form 0 over 0, which I can apply L'Hopital's rule to. So by L'Hopital, right, this is equal to the limit as x approaches pi over 4 of derivative of tangent is secant squared, so this is going to be negative secant squared x over derivative of cosine is negative sine 2x and then times 2, right, because of the chain rule. Okay, so in other words, we've got limit as x approaches pi over 4 of secant squared x over 2 sine 2x. So now what happens? Well, when we plug in pi over 4, okay, so you see, when we plug in pi over 4, I was saying earlier, like, this is what secant looks like. This is what secant looks like, but secant squared would give you all positive values back. Right, so secant squared would probably look something along these lines, right? Without any of this stuff down here. So it's going to positive infinity. So this thing's going to positive infinity now. Sine of 2 times pi over 4 is pi over 2, and sine of pi over 2 is 1. So this is just 1 times 2, which is 2. So we get infinity over 2, which is just infinity. So this is going to positive infinity. Interesting, right? So that's going to positive infinity there. I'm curious about that one, actually. I might want to take a look at that in Desmos, because that's really interesting. And I'm a little bit, I'm not too sure. Okay, so let's take a look at this in Desmos. So I'm going to look at 1 minus tangent x times secant 2x. That's what that thing looks like. Now we're looking for the limit as x approaches pi over 4. As x approaches pi over 4, we're definitely not going to infinity, are we? We're going to a finite value. What? I wonder what happened. 1 minus tangent x times secant 2x. This is interesting. This is interesting. Hang in there. I'm gonna cheat and look it up in the textbook. Why did this happen? Why did this just happen? So hold on. Oh, okay. It was just a mistake. Okay. So I led you astray. So look, this was a mistake in arithmetic when I got to the last step. I was still thinking about secant 2x. If you plug in pi over 4 here, 2 times pi over 4 is pi over 2, and secant of pi over 2 is undefined, right? It's either positive or negative infinity, like the limit. But this isn't 2x anymore, it's just x, right? Secant of pi over 4 is square root of 2, okay? And square root of 2 squared is 2. So my apologies, right? So this should be 2 in the numerator. And in the denominator, I think we said it was 2, right? 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. 2 times 1 is 2. So I apologize. This is 2 over 2, which is 1. That corresponds with our graph here, right? Okay. Something did seem kind of fishy about that, but anyway, we've got it worked out now. So, so my apologies. You're not going to trust me anymore. I make too many mistakes. No. Okay, here we go. Let's do another one. So, let's do limit as x approaches 0 from the right of 1 over x minus 1 over sine x. As x approaches 0, 1 over x goes to infinity. Sine x goes to 0, so 1 over sine x is also going to go to infinity. So this is an indeterminate of the form infinity minus infinity. Okay. So how do we fix this thing up, right? What do we do with these? So I think what we should try probably is the obvious thing, right? Try to combine these into a single rational expression. To do that, I would need a common denominator here. I would have to multiply by sine x. And here I would have to multiply by x. So I think I'm going to end up with sine x over x, or sine x minus x over x sine x. Now if we plug in 0, what do we get? We get 0 minus 0, which is 0, over 0 times 0, which is 0, right? So this is an indeterminate of the form 0 over 0. All right, we're in business, right? L'Hôpital. Okay, derivative of sine is cosine. Derivative of x is 1. In the denominator, we'll have to use product rule. So it's the derivative of the first times the second, plus the first times the derivative of the second. Okay, what do we get when we plug in 0 now? Cosine 0 is 1. 1 minus 1 is 0. In the denominator, we're going to get 0 plus 0 times 1, which is 0. So it's 0 over 0 again. Okay, well, that's alright. We'll use L'Hôpital again. Derivative of cosine is negative sine. Derivative of sine is cosine. And then here we're going to have product rule. So derivative of the first times the second plus the first. Oh, I'm sorry. Derivative of the first. Let me do this again. It's negative sine x over cosine x plus derivative of the first times the second plus the first times the derivative of the second. There we go. Okay. Now what? Now if we plug in 0. I mean, I suppose I could simplify this, but let's just check. If we plug in 0, we get 0 in the numerator, we get 1, 2, plus 0 in the denominator. So we get 0 over 2, which is just 0. Okay, so that's that one. Now you might be fooled into thinking that infinity minus infinity equals 0, but that's not true, right? That's not, it doesn't always work out that way. Okay, let's do another one. Okay, so let's see. If we plug in 0, from the left, 1 over x is going to go to negative infinity, and 1 over x squared is going to go to positive infinity. So this is negative infinity minus positive infinity. Well, that's not even indeterminate. That's just negative infinity. Okay? I mean, think about it, right? You have a really big number, and then you're subtracting off, or sorry, you have a really big negative number, and then you're subtracting off a really big positive number. That's just going to make a really big negative number, right? So that's just negative infinity. These two things are not exerting conflicting forces on the limit. So this is not even indeterminate, right? This is just negative infinity. So that's that one. I just threw that one in there to show you that, you know, infinity minus infinity is not always indeterminate. It's when you have like a positive infinity minus a positive infinity. That's indeterminate, right? Or if you have a negative infinity minus a negative infinity, that's indeterminate. Okay, so these two would be indeterminate. But if you have like a positive infinity minus a negative infinity, that's not indeterminate. That's just infinity plus infinity, right? That's not indeterminate at all. Or if you have, like in this case, we had a negative infinity minus a positive infinity. Again, not indeterminate. This is just negative infinity minus infinity, right? These are not indeterminate. Anyway, so that's that. Okay, and then I want to show you. What to do. I just have two more examples. I know that I've been going on kind of long, but two more examples. I want to show you what to do with indeterminates of the form 0 to the 0, 1 to the infinity, or 0 to the infinity. What we do with these is we try logarithmic differentiation. Okay, so we're going to try logarithmic differentiation. Let me show you how it works. So let's do limit as x approaches positive infinity of x to the 1 over x. Okay, if we plug in infinity, we're going to get infinity to the 0, right? So this is an indeterminate of the form infinity to the 0. So here's what we do with these. We're going to say let y equal limit as x approaches infinity of x to the 1 over x. Then ln of y is going to be limit as x approaches positive infinity of ln of x to the 1 over x. And why is that useful? Well, that's useful because we can bring down the 1 over x because of properties of logarithms. And then we can rewrite this as ln of x over x. And now, if you think about, well, if I plug in infinity, natural log of infinity is still going to be infinity. So I'm still going to get infinity over infinity. Or not still, I'm going to get infinity over infinity now. And so I can apply L'Hopital's rule. So I can say ln of y is limit as x approaches infinity positive infinity of derivative of ln of x is 1 over x. Derivative of x is just 1. And if I plug in infinity now, 1 over infinity is 0. So I just get 0 over 1, which is just 0. Okay, so ln of y is 0. What we wanted to find, though, was the limit of this expression right here, which we called y, right? So we really want to find y. We don't want to know what ln of y is. We want to know what y is. But it's easy to solve for y now, right? You just exponentiate, right? You just say that and get y equals e to the 0 power. Anything to the 0 power is 1, except for 0 itself. Right? So this limit here is 1. Okay, so kind of cool. Alright, and let me give you one more example of this. So we'll do limit as x approaches 0 of 1 plus sine x to the 1 over x. If I plug in 0, I'm going to have 1 plus 0, which is 1, to the infinity. So I'm going to get 1 to the infinity. So this is an indeterminate of the form 1 to the infinity, right? So that's not good. But I can use logarithmic differentiation again. So I'm going to say let y equal limit as x approaches 0 of 1 plus sine x to the 1 over x. And then take the natural log of both sides. Kind of cutting to the chase here and bringing the exponent down at the same time. Okay. Alright, now if I plug in 0, sine of 0 is 0, 1 plus 0 is 1, natural log of 1 is 0, so I get 0 in the numerator and obviously 0 in the denominator, right? So this is indeterminate of the form 0 over 0. I can apply L'Hopital. Derivative of ln of 1 plus sine x is going to be 1 over 1 plus sine x times the derivative of 1 plus sine x, which would be cosine x. And the derivative of x would just be 1. Okay, well now what do I get? When I plug in 0, sine 0 is 0, so I have 1 over 1, which is 1. Cosine 0 is 1, so I have 1 times 1, which is 1. I just get 1 over 1. So ln of y equals 1. That means y equals e to the 1, which is just e. So limit as x approaches 0 of 1 plus sine x to the 1 over x equals e. Okay? And that's that. So, L'Hopital's rule, very powerful, very good tool for us.